In this video, we discuss learning outcome number 2 for lesson 6.4, which is all about applications of the central limit theorem. Basically, we're going to want to determine whether the distribution of sample means may be approximated by a normal distribution, and then if a distribution of sample means may be approximated by a normal distribution, we'll want to compute probabilities associated with a range of values for sample means. So here are the requirements. The population has a normal distribution, or the sample size is greater than 30, then we can apply the central limit theorem and we can assume that the sample means are normally distributed. Now, if these requirements aren't met, there are other methods. They're just not discussed in this section, so the methods in this section will not apply. Basically, the idea is if the sample size is large enough, so if the sample size n is greater than 30, or if the original population had a normal distribution itself, the sample means are approximated well by a normal distribution. In that case, the mean of that collection of sample means, or the distribution of sample means, is equal to the mean of the original population, and the standard deviation of the collection of sample means is the population standard deviation divided by the square root of the sample size. When we're computing those sample means, we're just averaging a bunch of values from that original population. So we would expect that as we average lots of values, that variation would start to shrink. And that's exactly what we see here. As n gets larger, this sample standard deviation gets smaller. And then we also want to use this z-score conversion as we're looking for probabilities that sample means are greater than or less than or between two values. We're going to need to convert to the corresponding z-score. Now remember with z-scores before, we took an x value and we subtracted the mean of the distribution that it came from. And then we divided by this standard deviation in order to get that number of standard deviations from the mean. We're doing the same thing here, but this time, instead of having a random variable x from the population, our continuous random variable this time is the sample mean. So we've got x bar minus the mean of the sample means divided by the standard deviation of the sample means. And that's equal to the x bar in question minus the population mean divided by the population standard deviation over the square root of n. So here's a procedure for practical problem solving. The first thing you want to do is you always want to check the requirements. You always want to verify that the original population has a normal distribution so that we can assume that the sample means have a normal distribution, or that the sample size is greater than 30. If the original population does not have a normal distribution and the sample size is small, so less than or equal to 30, then we don't want to use the methods of this section. There are other methods, they're just not covered in section 6.4. Now, after you have confirmed that those requirements are satisfied, so the sample size is large enough or the original population was normally distributed, then we have to think about whether we're being asked about an individual value from the population or the mean from a sample taken from the population. If we are dealing with individual values, we'll use that z-score that we talked about way back at the beginning in chapter 3. We just take the x value, subtract the population mean, and divide by that population standard deviation. Now, if we're talking about sample means, we've got to use the mean and standard deviation of the sample means. And then we're thinking of that random variable not as an x value from the population, but as x bar. That's a particular sample mean. So our z-score is going to be calculated the same way. You just have to use the correct population parameters for the mean of the sample means and the standard deviation of the sample means. So we want the population parameters associated with that distribution of sample means as opposed to the distribution of the original population. Now, because of the relationship between the standard deviation here and the mean here, this simplifies to this formula over here. So this one on the right is the one we use in practice. Then once you have the z-scores and you've graphed your normal distribution and you've shaded either to the left or the right or in between a couple of values, and you're trying to find that probability, you do exactly the same thing that we did in section 6.1 and 6.2. You're going to find probabilities in areas, either using table A2 or Excel. So here's an example. Let's say we have females and we're told that their pulse rates are normally distributed with a mean of 74 beats per minute and a standard deviation of 12.5 beats per minute. In part A, we're asked to find the probability that one randomly selected adult female has a pulse rate that's less than 80 beats per minute. In part B, we're asked to find the probability that a sample of 16 randomly selected adult females has a mean pulse rate that's less than 80 beats per minute. So let's look at part A. In part A, we're asked about a single individual pulse rate for a single woman. So we don't actually need the methods associated with the central limit theorem at all. We're not talking about sample means. We're talking about a particular value from that population. So we're just going to do what we did in lesson 6.1 and 6.2. So we'll sketch a normal distribution with the mean that was given to us and the standard deviation that was given to us. Then we'll graph that X value that we're interested in, 80 beats per minute, and we're going to shade to the left because we're interested in the probability that X is less than 80 beats per minute. Or in other words, the probability that a woman has a pulse rate that's less than 80 beats per minute. So we do that. I believe this graph came from up there. It showed up in the little tooltip. It says mathcracker.com normal probability grapher. So if you want to graph one of these distributions just to get a better sense of what's going on, I would just search for normal probability grapher online, and you can find lots of graphers out there. This was the second one on the list. So I was able to graph this pretty quickly. So I graphed a normal distribution with the correct mean and standard deviation, and then I asked the grapher to graph to the left of X equals 80, and this is what it gave me. Now I'm trying to find that probability, so I want that area of that red shaded area that's right there. And we can find that area using either table A2 or Excel. So if I'm using table A2, I have to take that X value that we have and convert to the corresponding Z-score. And then we'll use table A2 to find the area to the left. So if I want to find the Z-score, I take my X value of 80, I subtract the mean of 74, and I divide by the standard deviation of 12.5, and that turns out to be approximately 0.48. Now remember, when you're doing this in your calculator, you want to do the numerator first, so put parentheses around that, and then divide by 12.5 in order to make sure your calculator gets the right answer. You have to be very explicit about the order of operations with your calculator. Okay, now that you have Z is equal to approximately 0.48, we say that the probability that X is less than 80 is the same as the probability that Z is less than 0.48. So we're saying X equals 80 is about 0.48 standard deviations above the mean. What is the probability that a particular X value is less than 0.48 standard deviations above the mean? Well, the area to the left can be found in our table. So I'll bring up table A2 now. So we go over here, and I'm looking for 0.48. So on the positive Z-scores, so there's 0.4, and there's 8 over here, so that's 0.08, 0.18, 0.28, 0.38, and 0.48. I don't know if you can see it. It's a little bit difficult to see. It's very small. 0.48 is right there. So there's the 0.4 and there's the 0.8. So the probability that Z is less than that 0.48 is the same as the probability that X is less than 80, and that is 0.6844 according to our table. Oops. Let me go back to my slides. Okay, so now you can do exactly the same thing in Excel. And here we want to use that normal distribution function. Now, the normal distribution function asks for inputs of the x value, the mean, the standard deviation, and cumulative area to the left or not. And we always say true for that one. With this normal distribution, you want to make sure you enter the correct mean and standard deviation of 74 and 12.5. So I would go to Excel, type equals norm.dist, open parentheses, 80. The mean is 74. The standard deviation is 12.5. I think the mean was 74. Yep, and I get 0.68438, and we round to 0.6844, which is exactly the same thing that we got using table A2. So that's how we handle part A. That was dealing with a particular X value, and we're saying if you randomly select one woman, what's the probability that her pulse rate is less than 80? And it turns out to be 0.6844 is the probability. Now for part B, we're asked for the probability that a sample of 16 randomly selected adult females has a mean pulse rate less than 80 beats per minute. So they're asking about a mean for a sample with n equal to 16 adult females in it. Now, because the original population is normally distributed, they told us that in the problem statement up here. Assume females have pulse rates that are normally distributed, etc. That means no matter what sample size we're dealing with, the sample means will be normally distributed as well. So that first requirement is met, even though n is equal to 16 and that's not greater than 30. So we can use the mean of the sample means and the standard deviation of the sample means. We can use those formulas that we had from before because the original population is normally distributed. Since the original population is normally distributed, so are the sample means. And the sample means will have the same mean as the original population and a standard deviation equal to the population standard deviation divided by the square root of the sample size. So we're going to do pretty much the same thing we did last time. This time we're sketching a normal distribution for the sample means, not the pulse rates themselves, but means of pulse rates, where we're talking about sample means for samples that have n equals 16 people in them. So the mean of the sample means is equal to the population mean, which is that 74 beats per minute. And then the standard deviation is that 12.5 divided by the square root of the sample size, which happens to be 16. And that happens to be a 3.125. So notice that that sample standard deviation it's 1/4 of the original sample standard deviation. So it's going to be very tall and skinny now in comparison to the original distribution. Then we want to graph x bar equals 80 beats per minute, and that's x bar because we're talking about a sample mean. Then we want to shade to the left since we're interested in that mean being less than 80 beats per minute. So we have this graph here. And the question is, what is that red area? You can use table A2 or Excel to find the area. So here, if we're using table A2, the first thing we need to do is we need to convert that sample mean to the appropriate z-score. And this time, since we're dealing with sample means, we have to use the mean of the sample means here and the standard deviation of the sample means here, which happens to be equal to the population mean and the standard deviation of the population over the square root of the sample size. When you fill everything in and you evaluate that, now you have a z-score of 1.92. So a sample mean of 80 beats per minute corresponds to a 1.92 standard deviations above the mean of the sample means in this case. So this time, x bar equals 80 is a lot more extreme value than x equals 80, where x would just be a particular person's pulse rate. Here we're talking about a sample mean when you have 16 people, that the sample mean is equal to 80 beats per minute. And that's more extreme because that z-score of 1.92 is much larger than that z-score of 0.48 that we saw in part A. Now, if I want to find the probability that x bar is less than 80, that turns out to be the same as the probability that z is less than approximately 1.92. And if we go to our table and we look this up, we get a probability of 0.9726. Let me show you in the table. So go to 1.9, 1.90, 1.91, 1.92. And then we see right there, that is the area associated with 1.92, 0.926. So that's how we would do that using table A2. Now we can also use Excel. Now, when you use this normal distribution function, they ask you for the mean and standard deviation of the normal distribution that you're talking about. Make sure that you use the standard deviation of the sample means here and not the sample standard, or not the sample or the standard deviation of the original population. If you use 12.5, you're going to get the same answer as you got last time. But since we're talking about sample means, that standard deviation is smaller. It's at 3.125. So if I go to Excel and I type equals norm.dist, I want x to be less than 80. The mean is still 74 because the mean of the original population and the mean of the sample means are the same. It's because the sample means are an unbiased estimator. And then the standard deviation turned out to be 3.125 when it was talking about samples of size n equals 16. And then we want to say, yes, we want a cumulative distribution. We want the area to the left. And we get 0.97257. And so that's 0.9726 when we round. So we get exactly the same answer with Excel that we got using table A2. Now here's our interpretation of the solution. It turns out that there's a probability of 0.6644 that an individual female has a pulse rate that's less than 80 beats per minute. So there's a 66.44% chance that a randomly selected female will have a pulse rate that's less than 80 beats per minute. But if we take a random selection of 16 females and we compute the mean pulse rate of those 16 females, then there is a 97.26% chance that those females will have a pulse rate that the sample of females will have a mean pulse rate that is less than 80 beats per minute. Now again, we are able to assume that the distribution of the sample means is normal. It's a normal distribution, even though n is equal to 16 and 16 is less than 30, because we were told that the original population of the pulse rates of females was normally distributed. If that wasn't the case, then it would not be appropriate to use this method and we would have to do something else. And that something else is not discussed in lesson 6.4.